Ach- Okay, so today we'll be making the tic-tac-toe bot. So before that, I'd like to give you a little bit of introduction to machine learning. So any one of you can tell me what do you think is machine learning? You can write in the chat also. Anyone? Okay, so machine learning is basically a field of when you answer pattern after repeating. Yeah, you can say that it's like that, but it's actually, you know, what is machine learning? It's a field of study that gives the computers the ability to learn without being explicitly programmed. Means it's like that we are implementing a pattern in the program. The computer is detecting the pattern and it's making predictions on its basis. Machine learning is a type of artificial intelligence. Yeah, it falls under the category of artificial intelligence. We are training the machines to make predictions based on input. So, what are some examples of machine learning? Means where we can apply them. Some applications include handwriting recognition, natural language processing. Then we have Amazon, Netflix recommendations that recommend us products based on our purchases. So that is also machine learning. And then we can use machine learning on medical records to predict diseases as well. So we have a lot of applications of machine learning around us, and it's a growing field nowadays. Machine learning and data science are the two most sought after computer science field nowadays. So again, machine learning algorithms are of two types: supervised learning and unsupervised learning. So, supervised learning is the type of machine learning in which we know that what is the output. We have a training set and we know that what each, for example, say if you have a value of x and we know that what is the value of y for that value of x, then that is called supervised learning. On the other hand, if we have a data set and we don't have the answers, means we have values of x, but we don't have values of y. We don't know what is the value of y for any of the x's. So in that case, the machine learning algorithms are called unsupervised learning. So we'll not be diving into that supervised learning or unsupervised learning. What we'll be doing today is an algorithm known as the Minimax algorithm, which can be used in games like tic-tac-toe, chess, checkers, etc. to help the computer predict the best possible move. So it's used in making game bots, as you might have guessed, the Minimax algorithm. So we'll be implementing that, but first we'll have to know two things before we can do that. That is, in this case, for example, if the computer is the one using the X symbol in our tic-tac-toe, then we'll refer to the computer as the maximizing player in this case. Now, why we are calling it maximizing player? Because in case of Minimax algorithm, we'll be setting a score to the computer. Now, if the computer is the one who is giving the X's, then the computer will try to maximize its score. It will try to, increase its score. So the X is known as the maximizing player, or the O if the computer is playing as the O, then the O is the maximizing player. But in this case, we consider the X as the maximizing player, or we can say it's the bot that will be playing. So again, similarly, O in this case will be the human who is playing against the bot, and the human will try to win the game. And if the human wins the game, the computer loses. So the human will try to minimize the score. So it will be so the O will be called as minimizing player or the human. Is this part clear? The maximizing player and the minimizing player? Okay. Acha. So now first we'll make a full tic-tac-toe game. So first we'll have to make our board. So our board will be like this. These will be the positions 1, 2, 3. Then we'll do something a pattern like this. Then again 4, 5, 6, and then again we'll repeat this pattern, and we'll have 7, 8, 9. So this will be our board design. You can also modify it by any way you like, but for purpose of simplicity we'll be keeping it like this. Now how we are going to print this board? For that we'll be making our own function. So I'll make a function def print board, and then we'll be taking the board as the input. Now in this case we'll be using a dictionary. You can also use list, but in that case we'll have to use 2D list, so that will become a little bit more complicated. So for keeping it simple, we'll be using a dictionary. We'll be using a board, taking the board as a parameter, and then see, here we have three values separated by these symbols. So what we'll do, we'll write print, then we'll first take the first element of the board. We'll give board 1, then this is string concatenation, we'll give this symbol plus, then we'll do board of 2, then we'll do this symbol again, and then we'll do board of 3. Okay. Now on the next line we have this. So I'll just take print, I'll just print this pattern because we just want this pattern in our board. So I'll just copy it. Next again I'll be doing this print statement, but for the positions, 4, 5 and 6. So I'll change the 1 to 4, then 5, then 6, then this pattern again, and then I'll be doing the same for 7, 8 and 9. So 7, 8 and 9. And then I'll just do a new line character for keeping the interface clean. So is this part clear? The print board function, how we are printing the board? Okay. Acha. So next we'll define a function. We'll call it def. Now we have to make a function to check whether a certain space in the board is empty or not. So for that we'll be using def space is 3. I am using camel case in the functions. You can also use underscores if you like it. And we'll be taking the position as the parameter. And our board will be a global variable, so we don't need that. Now, if board, and we'll check the position that's given to us. So board of position. Acha, I'll have to define the board first. So I'll just do that. I'll just define that board equals to, I'll form a dictionary. One is empty. Since our initial board is completely empty, so we'll be keeping all of these empty. 2, 3, then for 4, 5, 6, 7, 8, and 9. So we'll be forming the board like this using a dictionary, and we'll keep each of these empty because it's our initial board. Okay, now for checking if space is free, see, we are, for initializing we are given us empty, means we're giving a string with a space. So we'll check that if board of this position in the board is equals to the empty string. If it's so, that means the board is the space is free, so we'll return true, and else we'll return false. Okay, so is this function clear? The space is free. Okay, acha. So now we'll define a function for inserting a letter in the board. So let's make the function def. We'll name it insert letter, and then we'll need two parameters in this case, the letter and the position. So first we'll have to check that if the position of if that position in the board is empty or not. That's why we made the previous function. So we'll call it if space is free, then we'll pass the position. Position. Then we'll assign this letter to that position in the board. So we'll do board of position equals to letter. Okay, now we'll print the board. Print board, and we'll print the board. Okay, now we'll be calling a function inside this which we have not defined yet. So I'll now we can call it, I'll define it later. We'll call it if check for win. Check for win. We'll be making these functions in a bit. So if check for win, then we'll check which letter has 1. Now if letter equals x, now you remember that our bot is using the letter x. So if the letter if the bot has inserted the letter in the board and the check for win condition is true, so that means the bot has won the game. So if letter equals x, will print bot wins, and will be using the exit function. Now this exit function is used to break all the loops and just exit the Python program altogether. So we'll be using the exit function here. Now if this is not the case and the letter is O, that means the player has won the game. So print will say player wins. Okay, and we'll be calling the exit function once again. Now if this is not the case, and then if check for win is not returning true, then we'll have to check again that for the draw, if all the spaces are filled, we can say that the match is drawn. So we'll say if again I'll be defining the check draw function later. I'll just call it for now check draw. Now if check draw is true, then we'll print draw and we'll exit the program. And then I'll just use return if that is not the case to break the function. Now this part of the program was for if space is free. Now let's say if the space is not free, the user has entered a position that is already filled. So then we'll do else, we'll say print, and we'll say can't insert here, because the space is already filled, so we can't insert there. Now since the user cannot enter in that position, we'll have to again take the input of the user. So we'll say again position equals to int input, please enter new position. Now this will take the new input of the user, and then we'll again call this function inside itself. So insert letter, then letter comma position. Now this is again recursion. We have learned this in the previous week. Recursion. So we are using recursion here to again take the input of the user and again check for the validity of the move. So is this function clear? We'll be making the check for win and the check for draw function now. Is this one clear? The insert letter one? Okay. Acha. So I'll just take this one and I'll copy it here. Now we'll create the def check for win. So now in tic-tac-toe, if the rows are of the same element or the columns are of the same element or the diagonals are of the same element, then we say that the player has won. So we'll check those conditions one by one. So first we will do the first row 1, 2 and 3. So if both of 1 equals board of 2 and board of 1 equals board of 3, and we'll also have to check that the we'll also have to check that the position is not an empty string, because let's say we have this one, the first row is completely empty. So if we don't say that and position 1 is not equal to this one, then it will return that the player has won for this condition, which is not true. So we'll also have to mention that and board of 1 not equal to this space or empty. Now if this is the case, we'll just return true. So this was for the first row. Now we'll do it for the second row. If board of 4 sorry 4 equals board of 5 and board of 4 equals board of 6, and again board of 4 is not equal to the space, then we'll return true again. 4 equals 5, 4 equals 6, and board of 4 not equals to 6. Now similarly we'll just copy this one and make it for the other rows and columns. One row. Now this will be for the 7, 8, again 7, 9, and board of 7 not equals to the space. So this will be checking for all the rows. Next we'll have to do for all the columns. So I'll just copy it. Now for the columns we first have the positions 1, 4 and 7. So board of 1 equals board of 4, and board of 1 equals 7, and board of 1 not equal to that will return true. Similarly, we'll do 2 more times for the second and third column. So board of 2 equals board of 5. Again board of 2 equals board of 8, and board of 2 not equal to empty. Then we'll do for the third column board of 3 equals board of 6. Again board of 3 equals board of 9, and board of 3 not equal to space. So we'll return true. So that was for the rows and columns. Now we have two more cases for the diagonals, 159 and 357. So I'll just copy it 2 more times. And so first we have the diagonal 159. So I'll check board of 1 equals board of 5, and board of 1 equals board of 9, and board of 1 not equal to space will return true. And similarly for the second one we'll check with board of 7 equals board of 5, and board of 7 equals board of 3, and board of 7 not equal to space. So we are doing for this row, the first row, second row, third row, first column, second column 258, third column 369, first diagonal 159 and the second diagonal 753 or 357, any way you like. Now this was for the true one. If none of the conditions are followed, we'll else return false. Now, is this function clear? The check for win, the conditions we are putting inside the function. Okay. Oh, that was the check for win. Now we will have to make a similar function in this case. So I'll just copy it and I'll have to make a similar function that check which mark 1, and for that I'll have to pass a parameter mark. Check which mark 1 and I have to pass mark. And instead of these empty strings, what I'll do, I'll just one sec. So I'll just change the final condition, and for the final condition what we'll have to check, in the previous case we checked that the position was not equal to the empty string. So in this case we'll check that the position is equals to the mark which is passed as the parameter. That's the only difference. So if any of the condition is true, we'll check that this mark has won the game. And based on this function, we can tell whether the bot has won the game or the player has won the game. So that's the only difference between these two functions. So is this one clear? Okay. Now we'll have to make the check draw function also. So we'll check for draw now. We have already checked for one. So def check draw. Now we'll have to check for each key in present in the dictionary. In dictionary we have keys and key value pairs. So for example, in our dictionary, this 1, 2, 3, 4, 5, 6, 7, 8, 9, these are the keys, and these empty strings, these are called the values. So we'll have to iterate through each of the keys of the dictionary. So we'll use a for loop for that. For key in, now for getting the keys of the a particular dictionary, we can always use the dot keys method. So we'll use board dot keys. So this board dot keys will return me a list of all the keys that are present in the dictionary board. Now we'll have to check if board of key equals that empty string. Now if any of the key of the board is an empty string, that means that we have not yet reached the condition for the draw. So we'll return false. Now if that is not the case, that means after the for loop has passed and it has not gone to this condition, that means that there is no empty space left in the dictionary. So we'll just return true, because we have reached the terminal state of the dictionary and there is no empty space left. So is the check draw function clear? Okay. अच्छा. Okay. अच्छा. Next, we'll define another function, that is player move. When a player is making a move, we'll make it through this function. We'll do def, we'll say player move, and for the function, we'll say position equals to int input. And since the player is playing for the position O, so we'll say enter the position for O. We'll use an input statement to take the input from the user of the position he wants to insert the letter in. And then we'll remember we made this insert letter function to check whether it's a valid move or if it's invalid, we'll pass it through this insert letter function. Insert letter there, comma, position. And we are defining a player here. Our player is nothing but our bot is equal to this x and our player is equal to O. So if we change this, then we can also make player for x and bot is O. So we are initializing the variable player to O and we are calling it inside the insert letter function. So just give me one sec. Ah, so we are calling the insert letter here, player comma position, and then we'll just return. Player move function clear? This one? Okay. Now comes the interesting part. We are checking for the computer. We'll take the computer move and we'll make our next computer move. So, as I have said before, in case of the Minimax algorithm, what we do is we set an initial score. So, before that, we have three possible scores in each of the scenarios. If the player wins the game, the score is set to -1 because the player is the minimizing player. The human is the minimizing player. If the bot wins the game, the score is set to +1 because the bot is the maximizing player. And if the game is draw, the score is set to 0 because neither the bot nor the player is winning. So we'll have to initialize a score which is lower than -1. It can be any value which is lower than -1. And then we'll check for the best move that the computer can make. And based on that best move, we'll update the score. So now we'll make the next function def comp move. Inside the comp move function, we'll initialize the variable best score equals to, let's say I give -800. It can be any value which is less than -1. We can even take minus infinity also. For taking in minus infinity or using infinity in Python, we can do it like this: a equals to. We'll have to write float, and within inside the float, we'll have to give quotes, and inside the quotes, we can write -inf. So this will set the value of a to -infinity. But in this case, I'll be using -800. You can use any value, any negative value. So then I'll set my best move equals to 0 for now. Then I'll have to iterate through each of the keys present in our board. So again, for key in board dot keys, first I'll have to check whether the space is empty or not. So if board key equals space, if that is true, I'll set the board key to the bot. That means I am setting the key of I am setting this key of the board to an x. I am setting it to an x. Now will be calling a function here again, which I'll be defining after this one. I'll be calling it first. So we'll have to now say that the score is equal to, here comes our main algorithm. We'll say minimax. We'll have to pass in three parameters here. We'll have to pass the board. We'll have to pass the depth. I'm coming to it. What is depth and why we are using 0 here. And we'll have to pass in a value here again where that is maximizing or not. So usually when we start with minimax, we always start with is maximizing set to false, and with each turn we alternate it, false then true then again false then again true. So I'll be setting the is maximizing initially to false. Now the score will I'll get the score from the minimax. It will return either -1 or 0 or 1. Now I'll again restore the key of the board to what it was initially, that is space, because I'm not yet done. I'll have to check for each available position and I'll have to make the best choice. So I'll initially restore it here, and then we'll update the best score, because if the score is better than the best score, we'll update the best score. So if score greater than best score, then we'll set best score to score, and we'll set best move to the key. The key in which we are getting the score which is greater than the best score. So we are setting that key to the best move. Okay. And now after the loop has run for all of one sec. Best move key. Okay. So after the loop has run for all of the available keys present in the dictionary, I'll call insert letter. Then I'll say bot, because this is move of the computer, and I'll call in best move. So the bot will insert the letter in the best possible place it can find, and then I'll just return to end the function. Is this one clear? The comp move one. I'm coming to the minimax part. Okay. Now we have the minimax. Okay. So See, so in Minimax function will pass three parameters: the board, the depth, and the is maximizing. Now the board is the board which is the dictionary which we are passing. Now what is depth? Now in this case we can set the depth to be equal to 0. In more complex games like chess or checkers, for example, there are several moves for each stage. The bot is making a move, the possible moves the player can make. Then again, the possible moves the bot can make. So each level is the depth. The number of levels is the depth. We are initially setting it to 0. In this case, because in tic-tac-toe we don't have uh, a high number of possibilities, so we are just setting it to 0. In case of chess or in case of checkers, we can always set it to a custom depth to optimize the algorithm. So that was the depth. And the is maximizing part. The is maximizing, here we have set it to false. The is maximizing part alternates between the maximizing part and the minimizing part. The bot is making the move, then the player is making the move. So if is maximizing was set to false initially, in the next turn it will be set to true, because if the bot is making the move in this turn, the player will be making the move in the next turn. So is maximizing will change to true. Then again, if it's true, it will again change to false, because then after the player, again the bot will enter the move. So that was the is maximizing part and the depth. So in Minimax, Minimax will be requiring three parameters: the board, the depth, and the maximizing. Okay, now we'll define a minimax. Def we need three parameters, so we'll pass three parameters: board, depth, and is maximizing. Is maximizing. Okay, now first we'll be using will be, sorry we'll be using recursion inside Minimax. So first we'll have to mention the terminal states when the function will exit. So if check check which mark one bot. So first we are checking whether the bot has won the game, the final game after all the minimax part. The terminal state, if it's won by the bot, we will return 1. Because since the bot is the maximizing player, it will try to increase its score, and so we will set the score to +1. If means elif check which mark 1, and then we check it for the player. Now if the player has won the game after all the recursion, then we will return -1, and else we will do a check draw. Okay, no, since we are checking the draw here, we can use elif also. So I'll just use elif for check draw, and I'll do return 0 if that is the case. Now if none of the conditions are true, then we will come to the main body of this function. Now, the body of the minimax will be separated in two parts, is maximizing part and the minimizing part. So the first part will be if is maximizing is set to true. So if we will just say is maximizing, because see, in this case, if is maximizing is set to true, it will just take if true. So if true is true, so it will do this one, this part of the function. Now, since the name itself says is maximizing, so we are trying to maximize the score. So we'll be setting a initial score which is less than -1, and we will try to increase it as much as we can. So we will set best score equals to -800 again, which is lower than -1. We will check for key in board dot keys. We will check if board of key is equals empty. Then we will set a key to the bot, and then we will again have the score which will be equal to minimax. Again, here we are using recursion, minimax of board, and then we have set our initial depth to 0. So now we'll be doing depth plus 1 because we are increasing the depth, we are going to the second level. So we will say depth, the initial depth plus 1, and then as the final parameter, if is maximizing. So this part will execute if here instead of false, if it were true, then the is maximizing part will execute. So since it was previously true, so now it should be set to false because the next move will be made by the player. So I will say set the is maximizing variable to false because it was initially true. Now I will again restore the key of the board to be equal to that empty space one. I will check if score is greater than best score. I will set the best score to be equal to score, and we will do it for all the keys, and after all the keys have passed we will return best best score. So that was if is maximizing is set to true. Now we will do it if is maximizing is set to false, the part of the function that will actually, that will actually happen at the first iteration. So just tell me, is this part clear or not? This when is maximizing is set to true, is this part clear? How we are using the minimax algorithm here? Acha, okay. Acha, now we are coming to the part where if is maximizing is set to false. That means the move is of the player. The player wants to make the move. So now we will say, now since is maximizing is set to false, that means we are actually trying to minimize the score. So we will have to set a best score here which is greater than the highest possible score. In that case it was -800, which is lower than the lowest possible score -1. Here we will have to set a best score which is greater than the greatest possible score 1. So we'll have to set a best score which is greater than 1. It can be anything. So for consistency, I'll use 800 because I use minus 800 in that one, so I'll use 800 in this one. Now we'll do the same thing we did previously. So we'll do for key in board dot keys. I'll check that if board of key is equals to empty. In this case, I will set the key the key to be equals to player because we are minimizing the score. The player is playing. The computer is pretending to be the player and playing the next move to check all the possible moves the player can make. So I'll set the key to equal to player and then I'll again set score equals to, I'll be calling minimax here again, and I'll pass in board. I will do depth plus 1 because we are going one level deeper. So depth plus 1. And since here is maximizing was initially set to false, I will set it to true here. So this means in the next iteration it will again execute this first block of code where the computer is trying to maximize its score. In this block, the player, that is the human, is trying to minimize the score as much as he can. Uh, After calling the minimax again, I will be setting the key to equals. I will be restoring the key to what it was, the empty space, and then I will check if, since I am minimizing the score, I'll have to check whether the score is less than the best score. So if this is true, I'll be setting the best score to be equals to score. And then to end this block again, I'll be returning the best score. So that was pretty much the minimax part. So initially it will execute the second part. The player will try to minimize it. Then again for each for each key it will again call the minimax function. If none of this, if the board meets none of the terminal states, it will again go to these two blocks. So first this block will execute, then again this block will execute, then again in the next iteration this one will execute, and the cycle will continue until the function reaches the terminal state, which is either one of these three. So that was the Minimax algorithm. Now tell me if you have any doubts in this part. Is everything clear? Is maximizing part again? Yeah, sure. So in this case, the is maximizing part. So this part. If the is maximizing parameter is set to true, that means it's the turn of the computer. A computer is the maximizing player. It will try to increase the score as much as we can, maximizing the score. So for that, for checking that, we'll have to set an initial best score which is less than the lowest possible score, which is -1. So it can be anything. We can set it to minus infinity also. In this example, I'm setting it to -800, which is lower than -1. Now, for each key that is present in the board, I'm checking whether the key is equal to empty or not. if the key is equal to empty, in this case, I am initially setting the key to be equal to bot. Now, after doing that, I am again calling in minimax to do the next part of the recursion. So after coming in this part, the bot has played a move. Now what it will do in the next part, it will pretend to be the player and it will pretend to find the best move the player can make. And based on that, it will again go on the next iteration is maximizing part. The bot will play and it will check for the again the best move that it can make in order in so that the bot wins the game. So that's why we are calling minimax recursively to get the best possible score that the bot can have. Then we are again setting the key to what it was, that is an empty string. And since we want to maximize the score, we want to have the highest possible score that we can have. So we are checking that if score is greater than the best score, then we are setting the best score to be equals to score. And after that, after the iteration has been done for every key present in the dictionary, we are returning the best score, which is either 1 or -1 or 0. Now is it clear? Okay, so that was all our functions done. Now we just need to do the final bit and call them. One sec. Huh. So mm, we will first print the board, that is a dictionary. Initially we have an empty dictionary, so we'll be printing that. Now we'll be printing the instructions, that is computer goes first. Then we will print positions are as follows. And then we have to say the what are the positions, that is 1 2 3 4 5 6 7 8 9. Now we will do a new line character to make the interface clean, and then we have to set a variable first computer move. So we are doing this one first computer move, and we will set first computer move equals to true. Now why we are doing this, because if you want to make a more complex version of this game where you give the user the choice whether first the player will enter the score or the computer will enter the score, the computer will enter the first position. So in that case you can use the first computer move set equals to true. In this case, since we are for simplicity, since the computer always goes first, so we have set it to true. Now Now we'll have to run a while loop while not check for when. Now why we are doing this, we'll be running the while loop while the check for when is false. That's why we are using the not. If we just wrote that while check for win, this will not run only, because the check for win will initially be false until the computer, all the player has won. The check for win will return false. So we'll be using while not check for win. Since the computer goes first, I'll be doing comp move, and then after that player move. So that was it. Now fingers crossed this will run without any errors. Acha. Okay, the computer has made the move. Enter position for O. Let's say I give the middle position 5. The computer has made the move in the second row, in the second column of the first row. So let's say I'll try to block the computer 3. Now see, the computer is blocking me again on this move. It has checked for every possible move, and it has seen that if this space remains empty, then in the next move I can place a 0 here and win the game. So it's blocking me here. Now let's say I don't see that this space is empty, and I'll give the 0 here. So it's position 6. So see, the computer is entering the X in that position only where it can win the game, and it is winning the game. So our bot is working exactly how we want it to work. Now let's try to make a quiz draw. So let's give it an option. I'll give it an 7. Ah, it has won again. Because see, if I give it in position 6, it will give it in position 9 and win the game. Again, if I give in position 9, it will give in position 6 and win the game. See, it's giving in position 9 and winning the game. So actually, it is impossible to defeat this bot. What you can do is you can make a game draw, but you cannot win against this bot, because we are using the minimax function, and it will always give the optimal result. So that was it, the minimax algorithm, and tic-tac-toe bot. Now tell me if you have any doubts in any part of this program. I'll be sending it in the Discord server, this code, but if you have any doubt in any part, you can tell me. So is everything clear? Can you explain what is the depth again? Yeah, sure. So the depth in this case is basically the level in which we are checking. We are setting the initial depth to be equal to 0 in case of tic-tac-toe, because see, in tic-tac-toe there are not a lot of possibilities. So we are uh, initializing the depth to be equal to 0. First, when the bot is making the move, the depth is 0. In the next part of the minimax, again, since it's a recursive algorithm, in the next part, when the player is making the move after bot has made the first move, we are increasing the depth by 1 because we are going to the next level. After the player has entered the move, we are again checking for the bot's move, so we are again incrementing the depth by 1. So in this case, we are increasing the depth we are increasing the depth by 1 each time we recursively use the minimax algorithm. So that's where depth comes in. Though we are not using depth in this case, we actually use depth in more complex games like chess, where you can always set that if depth, for example, is greater than 10, then break the function, because otherwise it will run infinitely, because in chess there are quintillions of possible combinations. So depth is basically for optimization, but in case of tic-tac-toe we don't need it. If we don't write the depth variable, that's also fine, but I have made it just for generalized purposes. Now is it clear? Okay, so anyone else, any questions in any part? Okay, so no questions. Then we'll end here. So that was the last Python class. Hope you all enjoyed it. And if you want, you can join the tech club also. So in the tech club, I'll be teaching proper machine learning like linear regression, logistic regression, etc. If you want, you can join the tech club robotics department. And, if you do, then we'll again meet. So goodbye and thank you.